I want to bring up a few confusions and misconceptions. First, there's the basic thing. So this week I'm going to use another. Again, I'm using iPad, but now I'm going back to Word because it allows me to keep page lengths to be all the same. So first things is just basic relative motion. Issues, okay? You need to understand that there are two things. One is just relative motion, and relative motion is a very uncomfortable subject. I think the reason for that is that we're used to have all motion take place relative to the Earth, okay? And so when we are forced to think in abstraction, ship A, ship B, relative motion, we're not used to doing that. And it's just hard, it's a mind twister, just the relative motion. Not special relativity, not Einstein, not light, not any of that, just the relative motion. For example, here's a confusion. Student was asking, why is it that while according to Bob, Alice is moving from his back to his front, she's moving forward. Why is it that according to Alice, Bob is moving back? This is not special theory of relativity or any of that highbrow stuff. This is just relative motion. So imagine, close your eyes. Okay, you don't need to see me. Close your eyes. Imagine you're riding on a freeway in a car. Okay, close your eyes. Imagine that you're overtaking a bus or an 18-wheeler, let's say a bus. Now, if you are a passenger on the bus, you see the car, your car, pass from their back to their front and beyond. Okay, so you're passing them. But if you're a passenger in the car, what do you really see? Let's say it's a perfectly smooth road, and let's say it's night. You cannot see road, you cannot be distracted by trees, you cannot be distracted by anything else. All you see is just the lights from the bus. What is it that you will see? You will see bus moving backwards. Relative to you, the bus is moving backwards. So at one moment of time, the bus was in front of your hood. Then it's aligned with you. You see passengers right next to you. And then it ends up being behind your car. So that's the wonders of relative motion. So the idea that from Alice's perspective, Bob seems to be moving backwards, it's not a highbrow idea. And it is actually a good suggestion that while you're working through special relativity problems, in your mind's eye, you separate what's just an issue of relative motion and what's an issue of these weird effects from special relativity. So let me say more on that. So 2 is I want to remind you, what exactly do we mean by a measurement? Okay. Why is it that Bob needs an assistant if he's tracking Alice's clock? So here's Bob. Okay, so here's Bob. And here's Bob Jr. And here's Alice. Let me choose a different color. So here's Alice. This is moment 1. Well, let's say, okay, I will make sure that her ship is contracted like it was in the lecture. Let me see, I'm gonna choose the white color here. I'm gonna erase. Okay, so here's Alice. Okay, and Alice has her clock. So this is at T1, according to Bob. And then at a later instant of time, Alice is right here. This is T2. I guess I will stick to the black color. because this is time on Bob's clock. T1, and this is T2. Time on Bob's clocks. Okay, so if Bob wants to time the reading analysis clock, he's enlisting his assistant to peek at her clock when she passes by Bob Jr. Why is that? So your textbook has a wonderful discussion starting on end of page 9 and beginning of page 10. And I also discussed this probably at a couple of points. Remember this discussion of I take my axis and I line my axis with clocks. So every tick mark of my ruler has a clock endowed. Every tick mark of my ruler is endowed with a clock. Okay, so that's what Bob Jr. is. Bob Jr. is a clock that happens to be located at that event. So event 1, Alice, so here's Alice. Okay, so here's Alice, and Alice is passing by Bob. And event 2, let's say Bob, by Bob's front, by Bob's back window. Alice, event 2 is Alice is passing by Bob's front window. At that event, there better be a ruler, a tick mark on Bob's ruler and a clock right there and then. And remember, the reason that we're making measurements like that, rather than Bob looking with his eyes and tracking the motion of Alice, is that this form of measurement eliminates time delays. Because you see, we have these weird effects that clocks run slow and things like that. And one may be tempted to think that this is because of the time delay, or things that are synchronous in one frame or asynchronous in another frame. One might argue that this is, of course, this is because of the time delay, because it takes some time for information from the event to reach back to Bob, So to eliminate that layer of the time delay effect, we're making measurements like this. So now when we're finding that what's synchronous in one frame is not synchronous in another, that when Bob is tracking Alice's single clock, 2 units of time tick on his clocks while unit tick on hers, all of these effects are basic, they're deeper effects. They're not due to time delays. And more generally, let's say there is an event. Okay, so let's say here's a road. Let's say it's not a railroad. Not a road. Let's say it's a railroad, and right next to the railroad, okay, you have, so this is a railroad, and there's an explosion. It's an event. Boom, an explosion happens. Let's see, boom, explosion, okay? Now you observe this explosion from 2 trains. You have train 1 that's moving with 1 speed relative to the ground, and train 2 moving with another speed relative to the ground. Or you could say you have 2 trains that are moving relative to each other. I'm gonna make a train. The reason I chose a train is that you can imagine lining the axis of the train with rulers, right? Imagine the train, it's all moving in a straight line. So the giant coordinate system that's moving, and I'm not even gonna draw the train, I'm just gonna draw a coordinate system. Here's one coordinate system, S, and so this is moving with some speed relative to the ground. And there's another train, another coordinate system. I'm spreading them apart, but this is all in one dimension, okay? There's another coordinate system, S prime, that's moving with speed V prime. Let's say it's a bigger speed. At the moment when the event took place, according to S, it took place at position X. According to S prime, it took place at position X prime. And you might say, oh, that's trivial. Of course, X is not equal to X prime because they're different coordinate systems and their origins are constantly moving. And you're right. This is a trivial effect. What's not trivial is that the times are also different. So you see, you have the notion of relative motion in you. You understand that X is not equals to X prime because there's this distance right here, right, equal to VT. Let's imagine that V is larger than V prime. So I think this would be better. And some time ago, the origins were aligned at T0, but after some time has passed, the faster train in frame S has moved forward. These are all basic things. There's nothing tricky about this. What's interesting is that the T is also needs to be related between the two frames. That's what special relativity introduced. It introduced that time is not universal. Time is personal, just like space is personal. You're okay with space being personal. You're okay with X being not equal to X prime because the two coordinate systems are moving relative to each other. Well, it turns out that time is also not equal to T prime. T is not equal to T prime. But in any case, look, there's an event. At the point of event, you say, aha, the event took place at X comma T. And according to this frame, the event took place at X prime comma T prime. And to record that event, you need to have an assistant right here to mark the location of the event and the clock, reading of the clock. You might say, well, why do I care about reading of the clock here? Aren't all clocks in frame S prime synchronous? Well, they're synchronous according to X prime, but they're not synchronous according to S. I'm sorry, they're synchronous according to S prime, but not according to S. So when someone from frame S peeks into this clock, or they peek into this clock, or they peek into this clock, they will say, oh, all these clocks read different things. So the point is, when there's an event, you want to have an observer right there and then, right at the position of the event, and write down the value on the ruler of their coordinate system right there and then, where the event happened and when the event happened. And you do that in each frame. So that means you need to have an assistant or a robot that records the ruler marking of where the event happened in a particular coordinate system and the time when it happened in that coordinate system. So therefore, as one student emailed me, you don't have a situation like this. You don't have a situation where this is Bob and this is Bob Jr. and this is Alice. And Bob is looking at both of Alice's windows here and here. No, 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 no. You don't have things like that. If there's some event occurred here, let's say Alice has passed through some kind of a midway to Bob's ship, you better have an assistant right there and then to record the time and the ruler marking of that event where that event happened. So first of all, that's what we mean by an event, right? So right here, there's an event. And second, this avoids the triviality of time delays and all those kinds of things. Or put another way, even if you had only one single observer, no rulers and clocks lined up, when that observer receives information from events far away, they will need to recalculate what was the reading on clock and the marking on the ruler at the position of that event. which is equivalent to placing assistance everywhere. So that's the issue of measurement, and you need to understand this. This is very important. Okay, third issue, and this is the heart of the matter. This is concerning moving clocks run slow. What exactly does that mean? So I emphasized the notion of proper time. And your textbook also emphasized that. Pause the video. Ask yourself a question. Try to write down the definition of a proper time, a proper time interval. Okay, it's the interval of time between certain events in a frame in which the two events take place at the same location. Okay. Okay. When Bob is watching Alice, when Bob, with the help of his assistant, is tracking how long it took for Alice to brush her teeth. He is tracking one and the same Alice, who is located at the same location in her frame, but she will be at different locations in Bob's frames when she started brushing teeth, ended brushing teeth. When Bob observes Alice's one single specific clock, and he times the interval of time between when that clock strike 12 and that clock strike 1, stroke 1, he's tracking, with the help of his assistant, Alice's one and single specific clock that's located at one and the same location in her frame. And he's finding that while her clock went from 12 to 1, the clocks in his frame went from 12 to 3. That's time dilation. And only in this case does the time dilation formula apply, delta t. So we use proper time, we use tau for proper time. Only in this case, in this and only in this case, can you say that delta t equals gamma tau. Gamma is bigger than that. Okay, so track a pair of events that take place at the same point in frame S prime. So let's say X prime. And then while in S prime time tau passes, in frame S, a time delta t passes. It's very important that only when you're tracking a pair of events that take place at the same location in frame S prime, only in that case, delta t will be guaranteed to be larger than tau, where delta t is the timing between those same two events, LSS1 and LSS12 and LSS1, the time between those same two events in another frame. Evidently, delta t equals tau only when gamma is 1, i.e. the two frames are not moving relative to each other. Okay? Now, notice that if a pair of events did not take place in the same location as prime, and you timing the time interval between that pair of events in frame S, in general, you will not get time dilation. You might, there might still be a dilated time interval, but it actually could be just the opposite. So think about the following scenario, which I discussed at the end of lecture 8, part 1. What if Bob sits at the back of his ship and observes Alice's clocks as they pass by him? So he's not tracking Alice's multiple clocks. He's not tracking Alice's one clock with the help of his assistant, but he's tracking different clocks. Okay, so now imagine clock from Alice's front of the ship passes by him. He looks at that time and he looks at his clock, and then clock from Alice's back, from the back of Alice's ship passes by him. He looks at that clock. That's an extreme example because it's the reverse of the time dilation scenario, because now he's comparing the time interval on the clock which took place at the same location in his frame with two clocks in her frame. They're not at the same location. It's the reverse. It's exact reverse of the time dilation scenario. So now more time will pass on his clock than the difference in the reading on her two clocks. Does it mean that all of this is kind of it's an issue of technicality? No. When Bob observes Alice's EKG, her heart, or just not EKG, just her heartbeat, he really will think that her heart is beating slow. Okay, during her 1 minute, her heart beats 60 times. She has a 60 beats per minute in her own frame. But during his 1 minute, her heart beat only 20 times. This is a real thing. I'm not saying it's not a real effect. According to her, her heart is always at the same location. You're always at rest in your own reference frame. So if someone observes something on you, like your wristwatch, your heart, your breathing, they will think that that all of that is slowed down. If you're brushing teeth, that act always happens at the same location in your own frame. If someone co-moving relative to you observed it, they will think that you are going slow. It is a real effect. But that doesn't mean that everything that you observe from another frame will be slow, because if a pair of events in another frame did not take place at the same location, well, in general, you might actually get something that's faster. I gave an extreme example. Or actually, even you might get a reverse of the order of the order of events. You might actually get a reversal of the order in which events took place. Let's see why that happened. So let me write down one of the Lorentz transformations in the interval form. How do I get rid of this now? So I have delta t equals gamma times v over c squared times delta x prime plus delta t prime. Note that events took place at the same location in S prime if delta x prime equals 0, E1 and E2 happen at the same location in S prime, then voila, you get time dilation. But if delta x prime is not equal to 0, you might actually get all kinds of different effects. And in particular, if these terms have opposite sign, you might actually get a reversal of the order. So whether something is then slowed down or sped up depends on the details of how delta x prime and delta t prime are related. So let's say in Alice's ship, there are two flashes of light, one in the front of her ship and the other in the back of her ship. And let's say they're separated by 100 meters and they took place 1 second apart. Okay. So let's do the following. So I'm going to say delta t equals delta t prime times gamma times 1 plus v over delta x prime t squared delta t prime. I'm just going to rewrite this. Okay. So you see, then it matters exactly how delta x prime and delta t prime are related, and also the direction of her motion. If she's moving back, if her v is negative, in other words, she's moving along your x-axis in the negative x direction, and delta x prime is sufficiently large for a given delta t prime, or delta t prime is sufficiently small for a given delta x prime, then this whole thing can be more negative than -1. And then while delta t prime is positive, delta t can be negative. So you can get a reversal of the order. My point is, if a pair of events did not take place at the same location in Alice's frame, then not only can her 1 second be less than 1 second of your time, you can even get a reversal of the order. My point is, if you have a pair of events in Alice's frame that took place 1 second according to her clocks, it's not always true that those same pair of events are separated by more than 1 second according to your clock. It's only true if that pair of events took place at the same location in Alice's frame. I hope this gets through and makes things clearer. Time dilation is a real effect, but you cannot blindly apply time dilation formula to everything. Lorentz transformations, however, are more powerful and they apply to everything.